Okay. Okay, so let's begin today's session. So today is the third live interactive session of the course, NPTEL course, Applied Linear Algebra for Signal Processing, Data Analytics and Machine Learning by Professor Aditya K. Jagannathan from IIT Kanpur. So a brief short summary about myself. So my name is Yashvanth and I'm currently a PhD research scholar under the PMRF fellowship. I'm currently with the Indian Institute of Science with the EC department. My research advisor is Professor Chandra Murthy. He's also with EC department. So my broad research interests lie in statistical signal processing and its applications to wireless communications and optimization of communication systems. My current research focus is on intelligent reflecting surfaces for 5G and beyond wireless communications. So you can feel free to contact me over this email, which spells Yashvanth L at the rate of IISc.ac.in. And if you want to know more about me, you can always go to this link and know more about me. Okay, so I did not change this. So today we will basically be looking at some basics of um, we're going to look at Gram-Schmidt algorithms. Then we're going to look at some Gaussian random vectors, Gaussian random variables and vectors. And finally we're going to touch upon some eigenvalue properties. Okay. So that's going to be the agenda for today. Okay, so this is really going to be the agenda for today. We're going to look at the Gram-Schmidt algorithm, Gaussian random variables and vectors, and some eigen properties of matrices. Okay, so let me quickly go over the summary of the third week's lecture, which starts with the Gram-Schmidt orthogonalization. So what is Gram-Schmidt orthogonalization? So basically, given any set of linearly independent vectors or given a basis for a subspace, the goal is to find an orthonormal set of vectors which span the same subspace or same space as the original set of given linearly independent vectors. So this process of obtaining this orthonormal set of vectors is called, from a given set of independent vectors, called Gram-Schmidt orthogonalization, or it's also called Gram-Schmidt algorithm. The procedure for this kind of an approach is that, let's consider that we are given these input vectors x1, x2, and so on till xn. And then the goal is to find the orthogonal vectors from these given set of vectors x's. That is, namely that the output vector should be these guys, v1, v2, v3, and so on till vi or vn, whatever. So now the procedure to do is take any vector as the first vector. Let's say x1 is the first vector. Call the vector v1 is equal to x1 divided by norm of x1. So this will be the first vector in your orthonormal set. To find the second vector, what you do, you take the second vector in the given vector like x2 and remove the component of the vector x2 along the direction of v1. That in some sense that will produce a vector v2 dash which is orthogonal to the vector v1. Okay, so how to do that? X2 minus, take the inner product of x2 and v1. This is basically the it's called orthonormal projection. It's called orthonormal projection. Okay, basically you project the vector x2 on v1. That will give the component of the vector x2 along v1, that multiplied by the v1 vector itself. So this is basically the component of x2 along v1 direction. You subtract that from the second vector x2. The resultant vector is called v2 dash, and the v2 is defined as v2 divided by L2 norm of v2. v2. It's not v2 dash, it's v2. Oh, I'm sorry, it's v2 dash. It's v2 dash because you have v2 dash defined the second step. Yeah, it's v2 dash divided by L2 norm of v2 dash is given by v2. Okay. Now to find the third vector in the orthonormal set, take the vector x3 and remove the component of x3 along the directions v1 and v2. Okay. This will ensure that the vector v3 that you obtain, v3 dash, will be both orthogonal to v1 and v2. Okay, why did this get erased? Okay, so that is then you obtain the vector v3 by dividing v3 dash divided by the L2 norm of v3 dash. That will basically give the third orthonormal vector in the set of all orthonormal vectors, and so on. The ith vector in the orthonormal set is defined as, take the ith vector in the xi and subtract the component of the vector xi along all vj's where j ranges from 1 to I minus 1. That is, you basically subtract the component of the vector xi along all the previously formed vectors in the orthonormal set that you have in hand. Okay, and then you normalize the vi by vi dash by its L2 norm to get vi, and so on. You keep on doing. Okay, now let the resultant vector set of orthogonal vectors be v1, v2, and so on till vm. That is, I take an n such vectors xi, I ranges from 1 to n. Okay, and I take input as n vectors and I get m vectors as output, which are orthonormal in nature. Okay, now if n equal to m, that is, I get the same number of vectors as output. That's possible only if and only if x1, x2, and until xn are all independent. Okay, that is, in this case, if I feed the input to this Gram-Schmidt algorithm with all n linearly independent vectors, you will get output as m orthogonal vectors where m equal to n. That is, you'll get exactly the same number of orthonormal vectors. But you can also perform the Gram-Schmidt orthogonalization for linear dependent vectors also. I mean, you can always feed in linear dependent vectors. But what happens in that course is the number of vectors that you'll get as output, that is the number of orthonormal vectors that you will get as output, will be strictly less than the number of vectors that you feed as an input. So n is going to be greater than or n if the input vectors form a set of linearly dependent vectors. So this was about Gram-Schmidt orthogonalization. In fact, the first problem today is going to be related to this, and that particular is basically a matrix factorization that I'm going to talk about. And that particular matrix factorization is going to see a variety of useful use cases in many applications. So Gram-Schmidt orthogonalization is very handy and very important tool. So we'll take a good look at that today. Okay. Now the next notion that Professor had introduced is the notion of random variables, in particular on Gaussian random variables. Okay, so random variables are typically represented by a variable x, which is in uppercase letters. Okay, so x is a random variable. It's basically a Gaussian random variable whose probability density function is given by this particular expression. Okay, so probability density function tells, okay, suppose if I'm interested in the realization, if I call random variable x, and if I'm interested in the realization, the probability that this particular x will lie between a particular range, then what is the likelihood that this particular random variable x will take a range? To characterize such kind of chances, what is the likelihood or what is the probability? We need the notion of something called probability density function. What this tells is, in some sense, roughly, if I say fx of x, I mean this capital X denotes that I'm talking at denoting the random variable x, and the small x is the argument of this function. Okay, so if you input small x as a input, you get the output as this particular quantity. Okay, this particular function has two parameters, mu and sigma square. Right, it has two parameters, mu and sigma square. So this particular parameter, this function tells with what likelihood will I get a particular piece of will I get a particular number, little x. Okay, so now there are several characterizations that one can do to any random variable. In particular, I'm going to discuss some 3 to 4 characterizations, which are also been done by professor in the class. One is called the cumulative distribution function. So cumulative distribution function is defined as follows. It is denoted by capital F subscript X, denoting which random variable am I denoting. It is capital variable X of rho. So rho is basically the number, the input to this particular function. Okay, is defined as the probability that the random variable X takes a value less than or equal to rho. Okay, it's just a simple definition. In turn, if you compute this probability, the way to do is essentially compute this integral. Okay, the integral limits vary from minus infinity until rho, because I'm interested in all regions of x such that x belongs is at most rho. That means x can take minus infinity all the way till rho. So that is captured by this integral. And what is the integrand? The density function itself. And dx, I'm integrating with respect to the variable x. Okay, so this is the way how we can, the way to compute the probability of any event. And in particular, if I'm concerned about the event generated by this particular, and concerned with this event x less than or equal to rho, this is the value for that particular probability, which is called as a CDF. Cumulative distribution function is also called, it's also called CDF in short. Okay, any random variable is can be uniquely characterized by this CDF of the random variable. Okay, the next characterization is the expected value or the mean of the random variable. That is, if I have a random variable, okay, in every instance of time, it assumes a particular value. For example, if I toss a coin, I'll either get a head or I'll get a tail. If I associate a particular random variable with this particular experiment, and if I, let's say, x equal to 1 means I get a head, and x equal to 0 means I get a tail, right? And let's say with half chance, half of the times I get a tail and half of the times I get a head. Then the natural question is, what is the average outcome that I will be expecting out of this particular process? In other words, what is the average value that this particular random variable can take? That is captured by this notion of the expected value that a random variable can take, or it's denoted by E of x. Some people write it within a bracket, or just write ex. All are understandable, just understood from the notation. It's a calligraphic e, I mean, and it's a script e. So there's a 2 vertical bars to denote that it's an operator. So it's defined as this particular integral. So you just vary minus infinity to plus infinity as an integral limits x into fx of x dx. Okay, now for a Gaussian random variable, okay, its PDF is parameterized by 2 values, mu and sigma square. If you plug in the expression for fx of x in this integral, okay, and compute this integral, it will turn out to be mu. That is one of the parameters of the PDF of the random variable. That means what it tells is mu, which sits here, is really the expected value of the random variable, Gaussian random variable. In fact, today we will prove how this is true. Okay. The third characterization is the nth moment of a random variable. For example, if I'm interested in what is the energy content in a given random variable, then I would be interested in something called expected value of x square, right? Because it's something like very similar to norm square, right? So nth moment is defined as integral minus infinity plus infinity x power n times fx of x dx. So basically, if you put n equal to 1, it basically boils down to this expression, which means that the first moment of any random variable is its mean, that is expected value itself. Now, another very important characterization of random variable is called variance of a random variable. Okay, it's defined as this particular quantity. You take the expected value of x square, that is the second moment of the random variable, and minus it with the square of the expected value. Okay, so I've written down the actual integral. So integral x square fx of x dx minus integral x fx dx the whole square. If you compute this value, that gives the variance of the random variable. Now, what does variance of random variable indicate? It basically indicates the spread of the various outcomes a particular random variable can take. Okay, I think professor had very beautifully explained in the class that suppose if you draw the um, PDF of a Gaussian random variable, it looks like something like this, right? Okay, maybe I can draw. It looks something like this. Exactly if I draw this function fx of x as a function of x, it's exactly this function. It's an even function actually. It's symmetric about the y-axis. Now, if you see this, basically this main loop bit, that tells that all the values within this interval, assumes a higher value for likelihood. If you see the value that this particular x can take, this curve is very, very small. The y-axis is very small. But if you constrain your x values within this particular interval, the likelihood of any x occurring in this interval is very high. If you see the y-axis PDF value, okay. So in some sense, this particular main lobe will essentially tell with high probability any realization of the random variable x will lie in this region, and that particular region is called as is basically characterized by the variance of the random variable. So if the variance is very high, this width will be very high. The variance is very, very small, then what will happen is this width will no longer be this broad. It can rather become something like this. It will be very, very peaky, but the width will be reduced. You see the width here. The width here is small compared to the width here. Okay, so the spread or the dispersion tendency, or the deviation of how around the mean, how the random variable takes its outcomes is characterized by the notion of variance of the random variable. Okay, so there are applications. There are several applications of Gaussian random variables. In fact, the people, when they take probability theory as a separate course, there's a separate chapter on Gaussian random variables and Gaussian random vectors. It's a very, very important class of random variables. Some of the applications which are useful for this course are in terms of characterizing the noise that you have to encounter in any kind of a communication channel, and also in ML machine learning type of communications. If you want to model any kind of an observation, the first kind of modeling that comes to the hand is basically a Gaussian random based modeling. For example, in the lectures, the professor would have alluded to Gaussian classification and so on. Okay, so this is very, very important random variable. So the notation, how to denote a random variable, if I say that x and with a small tilde, some n, which is like a calligraphic n, in bracket with the parameters mu comma sigma square, it means that how to read this is x is a random variable that is Gaussian distributed with mean mu and variance sigma square. So by the way, just like how the parameter mu is given by mean, if you similarly compute this particular integral variance, you can show that the second parameter in the PDF sigma square will be the value. Okay, so if x distributed n comma of mu comma sigma square means x is a Gaussian random variable with mu and variance sigma square. So that is a way to denote and read it. The next particular topic is jointly Gaussian random variables. So the random variables x1, x2, and so on till xn are said to be jointly Gaussian random variables if for every value of alpha 1, alpha 2, and so on till alpha n in real numbers, the random variable summation over I equal to 1 to n alpha xi is a Gaussian random variable. So professor would have explained a slightly different way. He would have written down the multivariate probability density function of a random vector, and he would have explained if these random variables follow this multivariate PDF, then they are all jointly Gaussian. I'm giving here another way to basically check whether a given set of random variables are jointly Gaussian or not. It's a very simple, elegant tool that you can always use to check whether given set of random variables are jointly Gaussian or not. It's always possible that some set of random variables can be individually Gaussian random variable, but they need not be jointly Gaussian. You can always find examples. Okay, that's why it's possible to have random variables which are individually Gaussian but not jointly Gaussian. But if you have all of them are jointly Gaussian, every random variable has to be individually Gaussian. That is always has to be true. Okay, so the jointly Gaussian means you take any linear combination of any linear combination. The alpha is any number. Alpha can be any number in real numbers. any linear combination of the given random variables x1, x2, and xn, that the resultant should also be a Gaussian random variable. Okay? Then such kind of random variables is said to constitute jointly Gaussian random variables. Now, what is a Gaussian random vector? It's basically you take several Gaussian random variables and stack as a vector and get it as a random vector. But it's just little more than that also. That is, this vector is said to be Gaussian random vector if every element of the vector are jointly Gaussian with each other. That is, so this vector will have several elements, right? Let's say there are n elements. That means all these random variables x1, x2, and so on to xn have to be jointly Gaussian. They should not be just individually Gaussian, they should also be jointly Gaussian. Only then this vector is said to be a Gaussian random vector. Now, if a PDF of such a Gaussian random vector is given by this kind of an expression, and this is what professor would have told. So it's a random vector, x is a vector, and the input at a particular realization is also a vector. It's given by this particular expression. So n here stands for the number of elements of the vector. So this is the determinant of the matrix R. R is defined as a covariance matrix, and mu is the mean vector that is defined as this particular. That is, mean vector is defined as you take the mean of every individual random variables and stack that as a vector. That is the mean vector of the random vector. Okay, and again R is a covariance matrix which is defined as this particular vector matrix. You would subtract the actual vector from its mean. Okay, that will give x minus mu, and take the outer product, that is multiply x minus mu with x minus mu transpose. So x minus mu will be 1 n cross 1, and x minus mu transpose will be 1 cross n, and total will be an n cross n matrix. Okay, for example simplicity, if you consider mu to be 0, that is a zero mean vector, then R is equal to expectation of xx transpose. This is also called correlation matrix. That is, whenever mean becomes 0, covariance and correlation matrices are the same. So if I see the correlation matrix, it will look something like this. Just expand this. So this is nothing but expectation of x1, x2, and so on till xn times x1 and so on till xn. Just expand this matrix, you will get this particular matrix. Okay, this is an n by n matrix. Now, if the expected value of xi, xj equal to 0, that is for I not equal to j, then xi, xj are said to be uncorrelated. Okay. This is all these things professor had taught. And one property of covariance matrix is that it is a Hermitian matrix, meaning that a matrix is said to be Hermitian if this particular is satisfied. R equal to R transpose equal to R equal to R Hermitian. But in case covariance matrix is a a real matrix that is comprising all real numbers, then R equal to R transpose equal to R Hermitian. All are equivalent. Okay, a covariance matrix is always a symmetric matrix or a Hermitian matrix. Yes, is there a question?
Yes, sir.
Yeah.
Means Hermitian means R is equal to R transpose is RH. I
No.
couldn't get
Okay.
what's.
Okay. Let me clarify. Hermitian means A Hermitian is defined as A conjugate then transpose. Okay, this is how A Hermitian of any matrix defined as. You basically take the complex conjugate of every element in the matrix A and then takes the transpose of the resultant matrix. Suppose A is a real matrix, then A conjugate is same as A. That's why I wrote this. Suppose A is a real matrix, A conjugate is same as A, and then it means say that A Hermitian is same as A transpose. That's what I meant here.
Okay. Otherwise, it's A conjugate.
Yes, in general, it is R equal to R Hermitian. Maybe yeah, that's a good thing. I will maybe make it more explicit. R equal to R Hermitian if real matrix, then R equal to R Hermitian equal to R transpose. All are same.
Okay.
Okay. R Hermitian means you take R conjugate, then transpose it.
Okay. If it is a complex, then it is R star. What is it? Okay.
R star means, so if I have, let's say, let me take an example. Okay, so if I have, let's say, 1 plus 2, 2i, I, 2, and let's say 3 minus 4i. Okay, this is my R.
Okay.
Okay, So this is, let's say this is my A matrix.
Yeah.
It's basically its Hermitian is A conjugate is nothing but you take the complex conjugate of all entries.
All.
1 minus 2i minus
Okay.
I 2 3 plus 4i. Now take the transpose of this matrix, you get A Hermitian.
Yeah. Fine. Thanks.
Yeah. Okay. So another property is basically under the non-zero, sorry, if the zero vector, zero mean vector case, if mu equal to 0 and x1, x2, xn are uncorrelated, meaning that you have this particular condition satisfied, expected value of xi, xj equal to 0. Okay, if this is satisfied, then the matrix R will turn out to be the diagonal matrix. Okay, it's a purely diagonal matrix, and with each diagonal element having the number the variance of the corresponding random variable. That is, if I know that the random vector is x1, x2, and so on till xn, and if I know that all are uncorrelated with each other and individually they are all zero mean, then if I write down the covariance matrix for this, I will get something like this, where sigma 1 square is the variance of x1, sigma 2 square is the variance of x2, and so on till sigma n square is the variance of xn. Okay, so this is a property. So I need diagonal matrix. If you know that a covariance matrix is diagonal, then that means that it is a uncorrelated. So all the elements are uncorrelated with each other. The notation for a Gaussian random vector is, it's just same as basically what you saw in the single random variable case, except that now you have a mu vector instead of a mu single number, and instead of a variance which is single number, you have the entire matrix R. Okay, that is the only difference. Now, what is independence of random variables? So two random variables are said to be independent if they are PDF, that is joint PDF, can be written as a product of the two PDFs. So this is the PDF will productify. Okay, it's called the joint PDF is equal to product of marginal PDF. Marginal means you just take the PDF of one of the random variables. Joint means you take the PDF of the entire all the random variables together. For example, this is a joint PDF. You see here, this is a joint PDF because this is really nothing but I'm taking the x1, x2, and so on till xn. I'm jointly writing the PDF of all the n random variables which is abstracted by one vector. This is like a joint PDF. But we know that individually every element is a Gaussian random variable with PDF something like this. Okay. Now, if basically if I can show that you take any this is for any random variable, if you can show the two random variables are such that the joint PDF is same as the product of the marginal PDF, then these two random variables x and y are said to be independent. Okay. Now, in this context, what you can always show is if the random variables x1, x2, and so on till xn are jointly Gaussian, then this particular relation holds. That is, x1 through xn are independent. If I say that all these variables are independent, it is same as saying that these variables are also uncorrelated. Okay, it's a properties. Yeah, there are many properties which you may need to remember, but as you keep going through these points, it will get registered soon. Now, there's a very standard terminology that probabilist people use. If x1, x2, and so on till xn are independent random variables, but all of them have the same distribution. Okay. For example, if I take two coins, okay, I toss two coins independently. Now, if you see whatever coin I toss in the first, let's say I have left and right hand, and I toss two coins on my left and right hand. Now, the outcome that the coin toss results in the left hand will not impact or is completely independent of what the outcome will come on the right hand side. Okay, but if you see really both will have same distribution, because you cannot have the, let's say half the number of times you get ones and half the number of times you get zero. Right and right, both coins will get same distribution, same number of times they get zero, same number of times they won, yet they are independent. That is, one coin's outcome will not decide what will be the outcome of the other coin. So this is called IID. That is, they are independent and they have the same distribution. Then these random variables x1 to xn are said to be independent and identically distributed. They short form, they call it as IID, independent and identically distributed random variables. Okay, it's a very standardly used notion whenever you want to refer to some property of this random variable. The next topic is the linear transformation of random vectors. Suppose x is a Gaussian random vector, then y is equal to ax, that is where a is another matrix, is also a Gaussian random vector. And with mean, professor had proved in the class with mean such that it is equal to a times mu, where mu is the mean of the vector x, and covariance matrix Ry, that is the covariance of the resultant vector y, is given by A times Rx times A transpose, where Rx is the covariance of X vector. So these things professor had done detailed class, so I'm just skipping. Okay. So now, suppose y is equal to ax plus b. That is, I add another constant vector to this linear transformation. Okay, then what will happen is, and let's say x is distributed as a complex Gaussian random vector with mean mu vector and covariance matrix R. Then y is also a Gaussian random vector with the mean is given by a times mu plus b. That is whenever you add a particular constant to a random vector, the mean will also get added by the same constant. But the covariance matrix Ry is still given by A times Rx times A transpose. That is, B will not still affect. Whether you add B or not, covariance matrix will not change. That is, adding a constant does not change the covariance matrix. Now, the next part of the week was on eigenvalues and eigenvectors. So these are defined only for square matrices. So lambda comma x is said to be an eigenvalue eigenvector pair for a matrix A in C to the n by n if Ax equal to lambda x. Okay. Note that eigenvectors are always non-zero vectors. Non-zero means, I mean to say, it is always non-zero vectors. It can never be a zero vector. Okay, because you see, 0 trivially satisfies the equation. 8 times 0 equal to lambda 0. 0 equals 0. There is really nothing useful in it. So it trivially satisfied for any lambda, it's always satisfied. So eigenvectors are generally considered to be non-zero vectors. They cannot be zero vectors. Now the procedure to find eigenvalues and eigenvectors, we will do one example in class also today. So let's say Ax equal to lambda x. Okay, then bring a lambda x to left hand side, then Ax minus lambda x equal to a null vector, which means A minus lambda a times x equal to null vector. But since x and lambda are eigenvectors and eigenvalues, x cannot be a zero vector. Just now I told that eigenvector cannot be zero. Since x is not zero, there exists a vector x not equal to 0 such that the matrix A minus lambda I times x equal to 0. What does it mean? The null space of this matrix A minus lambda I should contain a non-zero vector other than the zero vector itself. That is, null space of the matrix A minus lambda I other than the zero vector itself is strictly not empty. It has some non-zero it has a non-zero vector inside this particular null space, and precisely we will see that those vectors are the eigenvectors of the matrix A corresponding to the eigenvalue lambda. So if the null space of the matrix has non-zero vector, what does it mean? The determinant of the matrix has to be 0. So if you see determinant of A minus lambda equal to 0, essentially if you expand this particular determinant, you will find that it's a equation in variable lambda with degree of the equation at most equal to n, where n is the order of the matrix. That is, if it's n by n matrix, you can at max it's a n by nth degree polynomial in lambda, and we just equate it to 0 and solve for lambda. Those lambdas are the eigenvalues of the matrix E. Now, how to find eigenvectors? From above, it's clear that eigenvectors of the matrix A corresponding to an eigenvalue can be found just by looking at the null space of A minus lambda, because essentially all these I'm interested in all these vector x, which lies in the null space of A minus lambda I. And these x's are precisely the eigenvectors. So the procedures first compute the eigenvalue by evaluating this determinant. Okay, you will get lambda 1, whatever roots that you get. And for every root that you get, compute the null space of this matrix. So for every every eigenvalue, you get a set of eigenvectors. And yeah, okay, that is how you come to the eigenvectors. Now, eigenvalue decomposition is such that you take all the eigenvalues in the diagonal matrix, stack all the eigenvectors as the different columns of the matrix U. Then you can show that under the premise that this particular matrix is invertible, A is equal to U lambda U inverse. Okay, this is very important. Again, we'll come back to it again in the later classes. This is also used to do something called similarity transforms. We will come back to it again. So this has a lot of application in the sense of, for example, if you want to compress a particular image, right, then you may want to basically express the same vector in different bases. In those kind of applications, you will basically go to something called similarity transforms and unitary transforms. Now, to understand them better, this is one of the good starting points. Okay, any matrix A, provided all the matrix which of all eigenvectors are invertible, can be written as U lambda U inverse, where lambda is the matrix diagonal matrix consisting of all the eigenvalues. An example of a rotation matrix which professor had given, if I have a vector U, and if I want to rotate this vector by a theta, if I want to rotate this vector by theta in anti-clockwise direction and get the vector V, then V can be written as A times U, where A is given by this matrix. It's a linear transformation. Okay? The property of the rotation matrix is such that it's a unitary matrix. That is A transpose equal to A transpose A equal to I. So in the same notion, what is a unitary matrix? A matrix A in C to the n by n is said to be unitary if A Hermitian equal to A Hermitian A equal to an identity matrix. That is, the matrix should have all the columns as orthonormal. It has all orthonormal columns, or it should also have, not or, and all the rows should be orthonormal. Only then this is a proper unitary square matrix. Some of the properties is that the determinant of any unitary matrix, U Hermitian equal to U Hermitian is always equal to 1. The eigenvalue of any unitary matrix will be such that the absolute value of eigenvalue is always 1. That is, basically it will lie on a unit circle because it's an equation of a circle. Okay, so the unitary matrix will always have eigenvalues which are located on the unit circle. The L2 norm is unitary invariant. That is, if you take any vector, you take x2. Okay, take its L2 norm x2. Multiply this vector by ux, where u is any unitary matrix. The norm, the resultant ux L2 norm is same as L2 norm of x itself. It's called unitary. The L2 norm is unitary invariant. Similarly, if there is any Gaussian random vector x, which is distributed with mean 0 and covariance sigma square I is the identity matrix. Sigma square means all entries have the same variance. Okay, which means what does it mean? X is a Gaussian random vector with all zeros and off diagonal, means all these vectors are uncorrelated with all the variances sigma square. That means all elements are independent and identically distributed. Okay, then for such kind of random vector ux, that is, you multiply by u, the resultant random vector, let's say y, will also follow the same distribution and now 0 comma sigma square I. Okay, so these are some of the properties and related summary of the class. So now let's jump into today's some of the tutorials and problems that are interesting to us. So the first question for today. Okay. Okay. So first question is visualizing QR decomposition as a way to perform Gram-Schmidt orthogonalization. Right. So professor had mentioned what Gram-Schmidt is, right? Now I'm going to illustrate with an example on how to find QR decomposition of any matrix A using the process of Gram-Schmidt orthogonalization. So what to do that. First, let me define what QR decomposition is. Any non-singular matrix. Just remember, matrix is said to be non-singular if the determinant is not 0. A can be decomposed uniquely in the form A equal to QR. That is, you can write any matrix A as a product of two matrices Q and R, such that number one, Q Hermitian Q equal to Q Hermitian equal to I. That is, Q is a unitary matrix. Okay. And number two, R is non-singular and upper triangular matrix with positive diagonal elements. Okay. So what this says is any matrix A can be, any non-singular matrix can be decomposed as product of two matrices Q and R, where Q should be unitary in matrix and R should be a non-singular upper triangular matrix with all positive diagonal elements. Okay, you can always find this decomposition for any non-singular matrix. Okay, I will write some applications of what applications the QR decomposition have. But before that, what I want to do is I want to first write down the Gram-Schmidt orthogonalization example for some example, and then I will tell how to write directly the QR decomposition using the results from Gram-Schmidt. Okay. Example. Let A equal to 101. Okay, maybe A minus 10 3 2 0. Okay. Okay, maybe this is really the first question. That's okay. Then find QR decomposition of A. Okay, so to that end, the solution is as follows. Okay, let first perform to the Gram-Schmidt orthogonalization to these vectors. Okay, what are these vectors? Column vectors of the matrix A. That is x1 equal to A1, the first column, same as 101, x2 same as A2 equal to minus 110, x3 equal to A3 equal to minus 320. Okay. So I'm just going to do the classical Gram-Schmidt orthogonalization, which professor did in the class. Let's call y1 equal to the first vector x1, which is equal to 101. Then y1 dash, which is like the orthogonal vector. Orthonormal vector is defined as y1 by norm of y1. It's nothing but 1 by square root 2 into 101. How did I compute? Norm of y2 equal to y12 equal to under root 1 square plus 0 square plus 1 square equal to root 2. Now what is second vector? Y2 equal to the second vector x2 and subtract the component of x2 along y1 times y1. Okay. Now what is x inner product x2 y1 dash? Nothing but x2 is nothing but minus 110 minus 110 times y1 dash is nothing but 101 with multiply 1 by root 2. This is nothing but minus 1 by root 2. Okay. So then substituting here, x2 is nothing but minus 110. Then minus into minus gets plus 1 by root 2 times is already another root 2 for y1 dash 1 0 1. This is nothing but minus 1 1 0 plus half 0 half equal to minus half 1 2. What is y2 dash, which is orthonormal vector? Nothing but y2 divided by norm of y2. It is same as 1 by 1 by 4 plus 1 plus
Hello,
4.
sir.
Yes.
It is 1 by 2, sir, last element.
Okay, yeah, 1 by 2. Yes. Yeah, thanks. So this is nothing but, I think this is same as 1 by root 6 times minus 1 to 1. Okay. Yeah. And y3 is nothing but the third vector x3, and remove the component of x3 from y1 dash and y2 dash. x3 comma y1 dash into y1 dash minus x3 comma y2 dash into y2 dash. This is nothing but um, minus 320, right? Minus 320. Then, okay, we need to compute these vectors. Okay, let's compute. What is x3 comma y1 dash? It's nothing but 1 by root 2 times minus 320 times 101, which is nothing but minus 3 by root 2, and x3 comma y2 dash is equal to 1 by root 6 into minus 320 into minus 121, which is same as 7 by root 6. Okay, so substituting these two values, and minus 7 by root 6 into 1 by root 6 of minus 121. Okay, now if you compute this, I get minus 320 plus 3 by 2 times 101 minus 7 by 6 times minus 121. Now this, if you just add them up, it becomes minus 320 plus 3 by 2, 0, 3 by 2 plus 7 by 6 minus 7 by 3 minus 7 by 6. This is nothing but, I think you can just make some calculations. Minus 2 by 6 minus 1 by 3 and into 2 minus 1, sorry, 2 by 6 into 3. 9 minus 7 is 2. 2 by 6. This is same as minus 1 by 3 minus 1 by 3 and 1 by 3. That is y3. Therefore, y3 dash equal to 1 by root 3 times minus 1 minus 1 1. Okay, so we have, what are the orthonormal vectors? We have done Gram-Schmidt now. Let's just write down what and all we have. y1 dash equal to 1 by root 2 times 101. Okay, next is y2 dash equal to 1 by root 6 times minus 121. Along with the fact that inner product of x2 comma y1 dash we found out to be minus 1 by root 2. Okay, then the third vector y3 dash equal to 1 by root 3 times minus 1 minus 1 1, with inner product of x3 and y1 dash equal to x3 and y1 is minus 3 by root 2, and x3 and y2 dash equal to 7 by root 6. 7 by root 6. Okay, so this is what we have, right? Now, what let me write down the expression for QR decomposition in terms of the Gram-Schmidt product itself. Okay, QR decomposition. Any vector, a matrix A is nothing but, okay, equal to A1, A2, so until AN. Okay, in this particular, I'm taking 3. Okay, it's a matrix 3, right? Because I'm interested in finding QR decomposition for 3 by 3 matrix. Okay, so this can be written as, let me just A3, A2, A3. I want to write it as QR, Q into R, right? Q is a unitary matrix. So what I will do is the Q matrix, I will just write Y1 dash, Y2 dash, Y3 dash. That is, I will take the orthonormal vectors written by the Gram-Schmidt orthogonalization. All these Y1, Yi dash will go as a column vectors as a matrix Q. This will be Q matrix. Okay. Now, how will R be defined? It's a non-singular upper triangular with positive diagonal entries, right? It's defined as follows. Take the inner product of A1 and Y1 dash. A1 and Y1 dash. Here, the second column of the first row is A2 and Y2 dash. A3 and Y1 dash. Then 0 because upper triangle. This is A2 and Y2 dash. A3 and Y2 dash. Now 0, 0. A3 and Y3 dash. So do you see the pattern? The pattern is that your Y1 dash will be fixed in your first row. Y2 dash is in the second row. Y3 dash in the third row. And you need to go in an upper triangular way. So from the first row, I will have A1, A2, A3 all be coming. The second row, only 2 and 3 will come. Third row, only 3 will come. This is the pattern. Okay. Now, all these now here, x is equal to A1, x2 is equal to A2, x3 equal to A3. So that's the thing. But these guys I already know. These values already was written by Gaussian elimination, Gaussian Gram-Schmidt orthogonalization. So use these values in these off diagonal entries. If you see this off diagonal, all these 3 entries are exactly given by these 3 parameters. Okay. Then let's just write it down. Only what remains to compute is these guys, these diagonal entries. But diagonal entries are easy to compute because I know the output. I know that these AI is the input. And y dash is the output, so I can easily compute. That is also a product that you can easily obtain from Gram-Schmidt. Okay, so if you just write it down, then what is the Gram-Schmidt orthogonalization? Equal to what is y1 dash? 1 by root 2, 0, 1 by root 2. Okay, y2 dash is minus 1 by root 6, 2 by root 6, and 1 by root 6. Then y3 dash is minus 1 by root 3, minus 1 by root 3, 1 by root 3. Now, what is the next matrix? R. Okay, A1, Y1 dash. Just take the inner product of A1, Y1. You can show that it is equal to root 2. Okay. Now, A2 and Y1 dash, inner product is same as AX2 and Y2 dash, which is same as minus 1 by root 2. Now, then A3 and Y1 dash, which is same as this guy. Same as minus 3 by root 2. 0, 0, 0. What is diagonal element? Next diagonal element is inner product of A2 and Y2 dash, which again you can compute it to be 3 by root 6. Now A3 and Y2 dash inner product is given by this particular value. That is same as 7 by root 6. And the last term you can compute to be 1 by root 3. Okay. So a matrix A, which was the original matrix 1 or made of all 101s, is now decomposed into the product of 2 matrices, which is called Q, is called R. And you can, just by performing Gram-Schmidt orthogonalization of matrix A, one can find the product Q and R. So this is called QR decomposition. You can verify, just multiply both the matrices and check whether you're getting the matrix A back or not. You can verify that it indeed gives matrix A back. Okay. Some applications of QR decompositions.
One question.
Yeah,
This Q matrix is a unitary matrix.
correct.
So we studied that this Gram-Schmidt orthogonalization will produce the uh, orthonormal matrices, right? Of
Orthonormal vectors, correct.
vectors. So both are same, right? When you say
Yes.
unitary.
So unitary matrix means each, if for example, if you see this particular column vector, okay, this guy is basically, if you compute the norm, it's unit norm. 1 by 2 plus 0 plus 1 by 2. I mean, squaring it. So it becomes 1. So this is a unit norm. This is also unit norm. This is also unit norm. At the same time, if you compute the inner product of these two vectors, right, column vector, it becomes 0. That means what? That is for any pair of column vectors. That is that is exactly what Gram-Schmidt gives. Gram-Schmidt, what it gives is, it will give us it will give a set of orthonormal vectors, meaning that every vector is mutually orthogonal, and not just that, every vector is unit norm also. That is precisely what a unitary matrix also should have.
Okay, thank you.
Yes. So applications of QR decomposition. So one is this, it's used to uncorrelate, the correlated data in machine learning techniques. For example, there's a very well-known technique called PCA, principal component analysis. And the underlying assumption is that you need to have the data, or the data will become uncorrelated after the um, after performing the principal component analysis, and then you pick the dominant component. So if you see the technique that is used in these kind of procedures, essentially QR decomposition will kick in. Okay, maybe professor will explain these PCA in the future classes, but that time again, I will, in the sessions, I will hint at how QR decomposition can be used in PCA. And some other applications include noise whitening in communication systems. Okay, so for example, there is a lot of, in any communication you will always have noise, and it's always better to have whitened noise to do further processing. So it's used in noise whitening. And third, in a proper linear algebra application, namely that in numerical evaluation of eigenvalues. Suppose if you are given a very very large matrix A in C to the n by n, it's an n by n matrix. Very, let's say n is, let's say what, maybe a 10 cross 10 matrix, right? 10 cross 10 matrix. So the procedure that I described here to find eigenvalue is basically compute the determinant of this vector matrix A minus lambda I. But what happens is, if you want to compute determinant of 10 by 10, we saw that it in turns, it's a very very complicated, very tedious procedure. So a numerical way to do that is obtain the QR decomposition of the matrix A, and then you do an iterative procedure, which I will explain maybe in future sessions. You can show that just by using QR decomposition, you can converge to the correct eigenvalues of the matrix. Okay, so this is about the first question. The second question is on Gaussian random variable. Okay, so if x is distributed normal mu comma sigma square, okay, that is fx of x equals 1 by under root 2 pi sigma square e raised to minus x minus mu square by 2 sigma square. X can belong to any real number. Prove that the mean of the random variable expected equal to mu and variance equal to sigma square. Okay, it's a bit tedious. I mean, it's a bit lengthy proof, but it's not very lengthy. It's just calculations are there. You can just follow, whether just follow the steps that I'm doing, and it's just calculation based the question. So to get familiar with how to do the integrals of to compute mean and variance. Now let's first see how to compute mean, that is expected value. So that by definition, e of x is nothing but minus infinity to plus infinity x into fx of x dx. So substituting for fx of x, minus infinity to plus infinity, x into 1 by root 2 pi sigma square e power minus x minus mu whole square by 2 sigma square dx. Okay, now replace x by x plus mu, which means dx is replaced by dx only. Dx is unchanged. Implies minus infinity plus mu is same as minus infinity. Plus infinity plus mu is same as plus infinity. You get x plus mu into 1 by under root 2 pi sigma square e raised to minus x square by 2 sigma square, because minus mu plus mu cancels and times dx. Okay, this I will just write as two components, minus infinity to plus infinity x into 1 by under root 2 pi sigma square e raised to minus x square by 2 sigma square dx, plus minus infinity to plus infinity mu into 1 by under root 2 pi sigma square e power minus x square by 2 sigma square dx. Call this as integral I1, call this as integral I2. So let's do computation of the first integral. Okay. This is given by minus infinity to plus infinity x into 1 by under root 2 pi sigma square e raised to minus x square by 2 sigma square dx. Okay, what I can do is I can split the limits. I will make this a 0, and then I will write the other integral 0 to infinity x into 1 by under root 2 pi sigma square e raised to minus x square by 2 sigma square dx. Now what you do is x replaced by minus x in the first integral alone. Then what will happen? It's nothing but minus of 0 to infinity x into 1 by under root 2 pi sigma square e raised to minus same x minus x square is same as x square minus x square 2 sigma square dx, plus the second term is as such. Okay, now this is same as, but what is this? See, this integral is same as this integral, except there is a negative sign. That means what does it mean? Same integral minus other integral means it's 0. I1 is 0. Okay, now we'll do I2 computation of I2. I2 is nothing but integral minus infinity to plus infinity mu into fx of x dx. Okay, so this is now what you do, replace x by x into sigma root 2, means dx will get replaced by dx into sigma root 2. Okay, then you can show that this becomes minus infinity to plus infinity mu into 1 by root 2 root pi e power minus x square dx, because this dx will become dx by under root 2, right? That will cancel that will cancel one sigma root 2 here. This is same as mu into 2 by root pi 0 to infinity e power minus x square dx, because we use the property that integrand, that is a function inside the integral, is an even function. So you can just replace minus infinity plus infinity as 2 times the integral 0 to infinity. Okay, but know that there's a particular relation that but this value 2 by root pi into minus infinity to plus infinity e power minus x square dx can be written as limit t tending to infinity 2 by root pi integral 0 to t e power minus x square dx. This is also called as this particular, this particular expression is also in the mathematics called as error function, ERF, at the upper limit t. This, if you go to numerical solution, this becomes 1. Okay, that means this quantity equal to 1. So what is left? Just mu. That is, then what does it mean? I2 equal to mu. But my original expected value is something but I1 plus I2. But I1 was 0, I2 equal to mu. So expected value equal to mu. Okay. Fine. Now, similarly, we'll compute the variance. Okay. So variance of x is defined as minus infinity to plus infinity, x minus mu the whole square, under root 2 pi sigma square, e power minus x minus mu the whole square, 2 sigma square dx. Okay. What I basically use this, we know that it is defined as expectation of x square minus expectation of x the whole square. You can show that this is same as saying expected value of x minus mu the whole square. This is also the same. Both are same. I use this particular definition here. X minus mu the whole square times the fx of x integral dx. Okay. Now you can check at your leisure. What I will do is basically x replaced by x plus mu. Okay. So what I will get is minus infinity plus infinity x square into, because x plus x minus mu plus mu is x square, 1 by under root 2 pi sigma square e power minus x square by 2 sigma square dx. Okay. Now x replaced by x into sigma root 2. Same trick as above. You can show that this becomes sigma root 2 integral minus infinity plus infinity sigma root 2 x square 1 by under root 2 pi sigma square or minus sigma root 2 x by 2 sigma square dx. This you can simplify, okay, and show that this is equal to sigma square into 4 by pi root pi integral 0 to infinity. I mean, basically it's 2 into 2 even function. Integrand is even function. Into x square into e power minus x square dx. Okay. Now put t equal to x square implies x equal to root t implies dt equal to 2x dx, or the same as 2 root t dx. 2 root t dx means dx equal to 1 by 2 root t dt. Okay. Then therefore variance of x, just the above integral, becomes sigma square into 4 by root pi into excuse me 0 to infinity root t square into 1 by 2 root t into e power minus t dt. You can write this as sigma square into 4 by root pi into half, because I'm just taking the half outside, 0 to infinity t power 3 by 2 minus 1 into e power minus t dt. Now again, from mathematics you can show that this is called as gamma of 3 by 2, okay, where gamma is the gamma function. Okay. You can numerically evaluate this gamma of 3 by 2 as, you can show that this turns out to be root pi by 2. Okay. 2, everything you can see equal to sigma square. Therefore, variance of x equal to sigma square. Okay. So we have solved 2 questions. I have 3 to 4 more questions with which we will stop today. But before that, let's take a short break. Now it's 7:12. We will meet back again at 7:17. Okay. So let's resume. Question 3. Okay. Let X and Y be jointly Gaussian random variables with parameters mu x equal to 0, sigma square x equal to 1, mu y equal to -1, and sigma square y equal to 4. Okay. Now rho is defined as a correlation coefficient. Okay, that is defined as the covariance of x comma y divided by sigma x sigma y, okay, equal to -half. Okay, what is covariance of x means expected value of x minus mu x into y minus mu y divided by sigma x sigma y, or this is also called as expected value of xy minus mu x mu y by sigma x sigma y. This is called the correlation coefficient between x and y. Okay, that is, if you remember, if this numerator is 0, then it's called covariance of xy is equal to 0. That means the x and y are said to be uncorrelated. That means if you compute the diagonal matrix, the covariance matrix, it will turn out to be a diagonal matrix. So now I'm saying it is not uncorrelated; they are correlated with a number -half. Okay, and the first question is, find the probability probability that the random variable x plus y is greater than 0. The second question is, find number a if a x plus y and x plus 2y are independent. That is, ax plus y is a random variable, x plus 2y is a random variable. I'm saying these two resultant random variables are independent. So what value of a will these two random variables are independent? That is the question. Okay. Okay, I hope the question is clear. You can note down the parameter values in your notes so that as I keep proceeding, it will be clear. Mu x is 0, sigma square x is 1, mu y is -1, and sigma square y equal to 4. The correlation coefficient, which is defined as the covariance of xy divided by sigma x sigma y equal to -half. Find probability that x plus y is greater than 0. First question. Second question is, find a if ax plus y and x plus 2y have to be independent. Okay, let's start the solution. First question is first. Okay, we'll start with the fact that sum of two Gaussian random variables is another Gaussian random variable. In this case, in fact, I told x and y are jointly Gaussian, means linear combination x plus y should also be Gaussian random variable. Okay, let that resultant u be the random variable x plus y. Okay, then I know that u is Gaussian. But what are the parameters of u now? We'll compute that. What are the parameters? We know that the parameters are given by mean and the variance. Mu and sigma square are the mean and variance. Okay, so expectation of y u is equal to expectation of x plus y. It is, you can write the same thing as expectation of x plus expectation of y. This is called as linearity of expectation operator. But I know expectation of x is nothing but mu x plus mu y. So what is mu x and mu y? 0 and -1. So expectation of u is equal to -1. Okay. Now variance of mu. Variance is little computational. Variance of u is nothing but expectation of u minus expectation of y, u whole square. That is same as expectation of x plus y minus expectation of u, same as expectation of x plus expectation of y. The same as expectation of x minus expectation of y whole square. Same as expectation of x minus mu x. That is, I'm grouping the terms y minus mu y. I'm grouping the terms. So this is like a, this is like b. So let's take a plus b the whole square. Expectation of x minus mu x a whole square plus expectation of y minus mu y the whole square plus 2 into expectation of x minus mu x into y minus mu y. Okay. This is same as variance of x, right? This is same as the definition of variance of x plus variance of y plus 2 times. This is nothing but covariance of x and y. This is nothing but variance of x is nothing but sigma square x plus sigma square y. This we know that plus 2 into, see, go back to the definition of correlation coefficient. This rho means rho equal to covariance of xy divided by sigma x sigma y, means covariance of xy is nothing but rho into sigma x sigma y. Rho into sigma x sigma y. Now we know all these quantities. Sigma square is x is nothing but 1 plus 4 plus 2 into 1 into 2 into minus half. Sigma square x is 1, so sigma x is 1. Sigma square y is 4, so sigma y is 2. 2 get cancelled, so this turns out to be 3. Yeah. So that means u is a Gaussian random variable with mean. What is the expectation value of u? Minus 1 and variance 3. Okay. So the question is, what is the probability that u is greater than 0? Which is same as 1 minus probability u is less than 0. But this is nothing but CDF of u, the accumulated distribution function. This is same as 1 minus, for those of you who know, this is same as 0 minus expected value of u by sigma u. This is same as 1 minus phi of 0 plus 1 by root 3. Same as 1 minus phi of 1 by root 3. What is phi? Phi is a function, okay? Phi is nothing but the CDF of the random variable x, which is Gaussian normal, Gaussian distributed with mean 0 and variance 1. You can always compute the CDF of any Gaussian random variable with arbitrary mean mu and sigma square. That is, what I'm saying is P of x less than rho. Okay, where maybe I'll write like this. Maybe I'll write the fact and then come back. Okay, fact. If x is a Gaussian mu comma sigma square, then P of x less than rho, which is nothing but the CDF, is same as phi of rho minus mu by sigma square, where phi of x is the CDF of y, which is normal 0 comma 1. Okay, this is always a, you just remember, note this for fact. You can prove this very easy. Sorry, this is not sigma, this is sigma. Okay, it's very handy. That's what I've used here. So here rho is like 0. This number is what? 0. That's why rho is 0. Okay, so you can now, for these, why I'm converting to these is these kind of CDF phi functions have numbers. Numerically you can evaluate. Okay, there's something called Clark's table, calculators, there are so many tables to evaluate these numbers. So this is given by approximately, you can show this to be 0.2819. What does it mean? The probability that u will become positive is 0.28. That is 28% of the time the random variable x plus y will realize the value which is more than 0. Now second question is find A so that ax plus y and x plus 2y are jointly Gaussian. Okay. Now, if you remember, we saw a property that if two random variables are jointly Gaussian and their covariances are 0, then it's independent. So that means it suffices to find the value of A it is sufficient to find A such that covariance of ax plus y and x plus 2y equal to 0. Because I know that they are jointly Gaussian, right? I know that they are jointly Gaussian. Then I just need to find, I mean, if I just prove that the covariance is 0, then they are also independent. Okay. Now we will now prove that. Covariance of ax plus y. Let's evaluate this expression first. Okay, this is same as, just carefully evaluate. Okay, please follow me, carefully follow me. Expected value of ax plus y minus expected value of ax plus y, the whole into x plus 2y minus expected value of x plus 2y. Okay, this is same as, okay, this is same as expectation of ax plus y minus a into expectation of x minus expectation of y times x plus 2y minus expectation of x minus 2 into expectation of y. Okay, this is same as, now this guy is equal to 0 because expectation of x mu x is 0. Similarly, this is also 0. This guy is what? Minus 1. This is what? Minus 2 because the mu y is what? Minus 1. So you can simplify this as expectation of ax plus y plus 1 into x plus 2y plus 2. Expand this now. There's nothing but ax square, means expand this product, ax square plus a 2axy plus 2ax plus xy plus 2y square plus 2y plus x plus 2y plus 2. Okay. Okay, I should say equal to 0, equal to 0, equal to 0, equal to 0, equal to 0. Same as saying, that you just now the 2axy and there's an xy here. Correct? Similarly, there is a 2y here, there is a 2y here. There is an x here, there is a 2ax here. Just combine all of them, it becomes a expected value of ax square plus 2a plus 1 into xy plus 2a plus 1 into x plus 2y square plus 4y plus 2 equal to 0. Now, what is the same as expected value of ax square, or a can come out? a into expected value of x square plus 2a plus 1 into expected value of xy plus 2a plus 1 into expected value of x plus expected 2 into expected value of y square plus 4 into expected value of y plus 2 equal to 0. Now we know expected value of x is 0. So this guy will go to 0. We know this is minus 4. Correct. And what is now we need to compute what are the variables remaining: expectation of x square, expectation of xy, expectation of y square. Okay. So first we'll compute them. Expectation of x square. It's nothing but sigma square x plus expectation of x square, because you know that variance is nothing but expectation of x square minus expectation x the whole square, which means expectation of x square equal to variance plus expectation of x the whole square. I know both these. This is nothing but sigma x square plus mu x square. This is nothing but 1 plus 0 equal to 1. Second quantity is expectation of xy equal to, how to compute this? I know covariance. Covariance formula I know. What is covariance formula? Given by expectation of xy minus expectation of x into expectation of y. But this guy is 0, right? So total will become 0. So covariance of xy is same as expectation of xy. But what is this? It's same as covariance. I know that I showed you that it's same as sigma x sigma y rho equal to expectation of xy. So what is this? Implies expectation of xy is nothing but 1 into 2 into minus half, which is same as minus 1. Third one is expectation of y square. Similarly to first one, it's same as sigma y square plus mu y square, which is same as 4 plus minus 1 square, which is same as 5. Now substitute all these variables or all these values in above equation. Okay. You can show that it boils down to a plus 2a plus 1 into minus 1 plus 10 minus 4 plus 2 equal to 0. You can compute it and you can show that a equal to 7. Okay, so for a equal to 7, the two random variables ax plus y and x plus 2y will be independent, because for this value of a, the covariance is 0. Since they are also jointly Gaussian, they are independent. I hope this is clear. Okay. The next question is as follows. Let x and y be jointly bivariate normal. That is jointly Gaussian. But in the bivariate means two random variables. That's why it's bivariate. Normal means Gaussian. Such that variance of x and variance of y are equal. Show that the random variables are these: x plus y and x minus y are independent. Okay, it's a solution. Okay. Now, what do we mean? Define the random variable z equal to x plus y and w equal to x minus y. So what should I prove? To prove z and w are independent. Okay. How to prove? First, let us establish that z and y are jointly Gaussian. So what is given? X and y are jointly Gaussian is given. First, we will prove that z and y are jointly Gaussian. Then what is the strategy? just prove that covariance of Z and W equal to 0. If I prove that, since Z and W are jointly Gaussian, Z and W are also independent. That's all. Proof is over. Proof. Now, so take any linear combination U is equal to alpha Z plus beta W. Why I am taking this? Because if I want to show Z and W are jointly Gaussian, one way to do that is take the linear combination of the two random variables and show that for any linear combination, it's a Gaussian random variable. Okay, so I'm taking one particular instance, alpha and beta, as a linear coefficients. It is nothing but, now substitute for Z. Z is nothing but x plus y. Beta times x minus y. This is nothing but alpha x plus alpha y plus beta x minus beta y. Now group the terms which are common to x. That is alpha plus beta times x plus alpha minus beta times y. Call this as alpha prime and this is beta prime. But since x and y are jointly Gaussian, that is given. Implies alpha bar x plus beta bar y is Gaussian. Okay, since it's true for any alpha bar and beta alpha prime and beta prime, that means it is true for any alpha and beta also. Implies Z and W are jointly Gaussian. Okay, fine. This is important. Step 2, compute the covariance between the random variables. Okay, let's do it step by step slowly. This is same as covariance of x plus y and x minus y. Same as covariance of x plus y minus expectation of x plus expectation of y times x minus y minus expectation of x minus expectation of y equal. That's all. Okay. This is nothing but covariance of, I'm sorry, this is expectation, right? No more covariance. This is expectation. This is nothing but expectation of x minus expectation x plus y minus expectation y. I'm just grouping them within the first term. Similarly, in the second term, x minus expectation x minus y minus expectation y. Okay. Now this is what A, B, A, B. So what is this of the form? Expectation of A plus B into A minus B. That's something but expect A square minus B square, right? Expectation of A square minus B square. What is A square? Expectation of x minus expectation x square minus expectation of y minus expectation y square. Now, can anyone complete the proof now? See, what is given? Variance of x and variance of y are equal. Now, can anyone complete the proof? Would anyone like to try?
It needs some more previous exposure. Continues.
No, this is a definition, right? This is a definition of variance of x.
Okay.
This is the variance of y. That's what I wrote here.
Okay.
So here, if you go back, I wrote here that is a property. If you see, variance of x nothing but expectation of x square minus expectation of x the whole square. That is same as expectation of x minus mu the whole square. But what is mu? Expectation of x only. So it's like expectation of x minus expectation x the whole square is same as variance of x.
Expectation of x is
Mu.
Yes.
So mu is nothing but expectation of x.
Yes.
Right. So what does it mean? This is same as expectation of x minus expectation x square.
Yes. Square.
Correct. That is nothing but variance of x.
Correct. Yes.
Now you see here what I have. I have the same thing here.
Okay. Yes. X minus mu is expectation of x.
So, but I know the question says variance of x is same as variance of y, and I have a minus, so this is 0. Right? So what I have proved, I first proved that z and w, that is x plus y and x minus y, they are jointly Gaussian. And then I proved that the covariance of x plus y and x minus y are 0. I proved both of them. That means it should imply that x plus y and x minus y are independent. That's all.
Okay.
These two. Is this clear?
So Ex is actually mu, so that is mu and Ex is interchangeable.
Sorry, can you repeat?
Yeah, Ex, expectation of x, and mu is interchangeable. Both are
They are
same.
same. Exactly, they are same. In fact, this is same as. Okay, let me write. Oops. This is same as mu x.
Yes.
This is same as mu y, equal to mu y. This is the definition of variance. So again, maybe write. Here is a different color. For any random variable x, variance of x equal to expectation of x square minus expectation of x the whole square, same as expectation of x square minus mu x square, same as expectation of x minus expectation of x square. Okay, let me write it again. Same as expectation of x minus mu x square. All are same. All four are same quantities.
Okay. Yes. Okay.
Okay.
Yeah. So here the second part becomes the same as first part, so that it becomes 0.
Correct, correct. First term is same as second term because the question says variance of x equals variance of y.
Okay.
So they become 0.
Okay.
Okay. In fact, this is not very, very difficult. I mean, you need not memorize. In fact, let me show how this is true. Okay. If you say expectation of x minus expectation of x, let me just expand this. Okay. This is same as expectation of x minus mu square, because mu is used to denote that it's a mean of the random variable x, mu x. Now let me just do a minus b the whole square. This is same as expectation of x square plus mu x square minus 2 into x mu x. Correct?
Yes.
Now this is same as, take linearity, means this same as expectation of x square plus expectation of mu x square minus 2 into expectation of x into mu x. But you see, expectation is defined for a random variable. Only if there is some randomness, I will ask what is the average value of the random variable. But I cannot ask what is the average of average. Average is already a deterministic number. So that it doesn't make sense to call average of average. So this is same as expectation of x square plus expect mu x square is a constant. Correct? Because basically mu x is nothing but mean of the random variable. That is the average of the random variable. Now, average square is a deterministic quantity. I cannot ask what is the average of average. So this is same as mu x square. That is expectation of a constant. If I tell that a number is a constant, let's say 2, what is the average value of 2? It is same as 2 itself. 2 cannot have different realization. 2 means 2. Means expected value of any constant is a constant itself. Same way here, mu is a constant, so that will come out of expectation. The same as expectation of x. This is nothing but expectation of x square plus mu x square minus 2 mu x into what is expectation of x? Same as mu x again. Nothing but expectation of x square plus mu x square minus 2 mu x square. Same as expectation of x square minus mu x square, which is same as expectation of x square minus expectation of x the whole square, which is same as this, whatever I wrote here. So all are synonymous. All are all definitions are just same. In which context you want to use which expression to so that you can easily simplify your answers. That only depends. Is that okay? I think someone asked whether it is all fine. Is that okay?
Okay, sir.
Yeah. So all are equal in definitions. You just have to use whichever you want in different context. Okay. So next is on eigenvalue properties. But again, I'm telling, so the whatever I'm solving are all very related to class materials. I mean, this is basically to supplementary to the class material. Okay, but all the exams will be very. So what the motive behind me doing these sessions is so that if you understand these kind of problems, the examinations and the assignments will become extremely simple. That is the reason why I'm doing these kind of problems. Okay, so the next question is this is question 5. Okay, let lambda and x. Okay, maybe I will say show that eigenvectors. I'll write full form. Eigenvectors corresponding to matrix A. Sorry, corresponding to eigenvalue lambda of matrix A is not unique. That is what I'm saying is that is if Ax equal to lambda x, I am saying that there can always exist another y such that ay equal to lambda y not equal to x. You can always find such y such that x is not equal to y and still both are satisfied. That is what I'm trying to ask. It's a very simple. So what it says is eigenvectors are corresponding to any given eigenvalue are not at all unique. You can find many eigenvectors. Okay. Solution is very simple. Okay. So since let x be the eigenvector. So I will write E vec. Okay. Corresponding to eigenvalue eval lambda of A, so that Ax equal to lambda x. Multiply by C on both sides. C, it's a some real number. Then what will happen? C into Ax equal to lambda C into x. You can write this as A into Cx equal to lambda into Cx. Call this as y. Okay. If C is not equal to 1, implies what? X is not equal to y. But still, Ax equal to lambda x and Ay equal to lambda y. Okay. Therefore, X is not unique. That is, you cannot have just one eigenvector X corresponding to eigenvalue lambda such that Ax equal to lambda X. In fact, all the eigenvectors, how is Y related to X? It's just a scalar it's a scaled version of the vector X with the same, which gives the another vector Y. What does it mean? And see, I did not restrict to any particular real number. It's any real number, right? So let's say X equal to 1, 0. Then, or maybe 1, 2. Then Y equal to, let's say, into 2, 2, 4, or into 3, 3, 6. All of these are valid eigenvectors for the same eigenvalue of the matrix. So eigenvectors are not unique at all. Okay. In fact, you can have, if you do that, C is any number, right? You can multiply by any C. That means you can find infinitely many eigenvectors for the same eigenvalue of the matrix A. Okay. This motivates to the definition of what is called, definition of eigenspace. Okay. It says the set of all vectors, set of all eigenvectors, okay, of A, which is a n by n square matrix corresponding to an eigenvalue eval lambda is called eigenspace of the matrix A with respect to the number lambda, eigenvalue lambda. Okay, denoted as E lambda. That is, it's a set of all vectors. The set of all, of course, since eigenvector is non-zero vector, it's a non-zero vector such that Ax equal to lambda x. Okay, so eigenspace. Okay, property E lambda. Okay, E lambda, which is defined as E lambda union the zero vector, because this vector as such doesn't have any zero vector, but you just add zero vector to this space E lambda, you can show that this particular set E lambda naught is a subspace. It's a vector space, a subspace of Cn. That is, in the end, it's a vector space for spanning a subspace in an n-dimensional space. Okay. Now we saw the values, how to compute eigenvalues and eigenvectors. Now maybe what I will do in the remaining 5 minutes is quickly I will give maybe, okay, this is a little long example. Maybe I will do this in the next class. Okay, and there is another problem. Okay, I will do one thing. Let's stop here for today. I will start with a numerical example of computing eigenvalues and eigenvectors using this definition. That is, determinant of A minus lambda I equal to 0. And eigenvectors can be found from the corresponding null space of A minus lambda. Using this concept, I will find eigenvalues and eigenvectors of a 2 by 2 matrix. Okay. And then we will see some very important property of eigenvalue, namely that suppose, for example, if I know that, okay, if I know that A, matrix A has a eigenvalues lambda 1, lambda 2, and so on to lambda n, how will the eigenvalue of A square be? Is there any relation between the eigenvalue of A square and A? Is there any relation? How will the eigenvalue, for example, 5A be? Right? All these, any polynomial in any polynomial, for example, equal to 7A cube minus 6A plus 2y. If I define some matrix polynomial like this, okay, that is what I'm saying is you take A, let's say A equal to 2, 0, 1, 1, okay. Then you do 7 into 2, 0, 1, 1 cube plus 6 minus 6 into 2, 0, 1, 1 and plus 2 into 1, 0, 1, 0, 0, 1. So this will give rise to some matrix, let's say A, B, C, D. How is the eigenvalues of A, B, C, D related to the eigenvalues of A? So these kind of properties, we will start with the next. We will introduce in the next session, and then we will move on to the problem tutorials for the next week's this week's lecture series. Okay. So are there any questions? Maybe we can discuss any doubts that you have in today's problem. We can discuss for some time, and then we can stop for today. Are there any doubts in the way I computed covariance of x comma y? For example, the variance definitions. Please ask. This is the right time. We can spend time and I can explain. Yeah, there's a question.
So it's all this like a basic understanding of a probability and Gaussian random variables, right? And with that, we will be able to proceed these parties.
Yeah, I thought the professor had mentioned very basics of Gaussian random variables in the lectures, right?
Okay. Yeah.
Sorry?
For reference, we can see any probability related books also.
Yeah. So see, if you, for example, any first course in probability, any basic book will contain these kind of characterizations. So for example, what I'm saying is, what are important for basics are, we should know what is mean of random variable, what is variance, what is covariance. So mean is defined for one random variable. Variance is defined for one random variable. Covariance is defined between two random variables. Okay. Similarly, correlation, that is same as covariance of our two random variables if the random variables are zero mean. These are very basic, actually, some mechanics. Just need to know the definitions and the corresponding mechanics. Just remember, okay, covariance is same as correlation if mean is zero, and like this, then it gives a correlation coefficient. All these are basic definitions, and that's what today I also introduced. So mean is nothing but expected value of x, which is same as integration x into fx of x dx. Variance is nothing but expectation of x square minus expectation of x the whole square. You can again write on the integral. So these are actually definitions. Okay. Yeah, but I do understand for some people who do not have even basic probability background, maybe just these concepts, whatever professor had introduced in the class is sufficient. Okay, that is enough for solving all assignments. Not very hi-fi is needed. And by the way, how are the assignments going? Is it going fine? Or do you feel like I need to solve some assignment problems, graded assignment, already over assignment problems, or anything like that? I mean, if there is any such request, please always let me know. I can always quickly go through the solutions of every assignment. Okay, let me stop recording.